Ladies and gentlemen, I think we can get started. My name is Armagan Al-Haq. I am the Manager of Program Development, Partnerships and Finance at the Waterloo Institute for Sustainable Energy here at University of Waterloo. And today I would like to introduce you to our guest speaker, Professor Wu. He is an assistant professor in the Department of Mechanical and Mechatronics Engineering at the University of Waterloo. He has received his bachelor's and master's degrees from Zhejiang University and PhD from MIT. His research group, Greener Production at Waterloo, combines expertise in thermal science, material engineering, and techno-economics to develop sustainable technologies for energy conversion and chemical production. Ladies and gentlemen, please welcome Professor Wu. Professor Wu, the stage is all yours. Go ahead.
Thank you. Thank you, Armagan, for the kind introduction. Hello, everyone. My name is Xiaoyu Wu. I'm an assistant professor in the Department of Mechanical and Mechatronics Engineering. Today is my great honor to be here to give you a brief introduction of what we are doing in my lab, Greener Production at Waterloo. In the labs, we are dealing with different type of production solutions for chemicals and energy. Currently, we are working on 3 different topics. The first one is hydrogen production technology and systems. We are developing a pressurized hydrogen production system that will decrease the energy consumption for the downstream compressor for the hydrogen gas. And also, we are looking at solar to hydrogen reactor design. In this case, we want to understand the kinetics as well as the flow dynamics inside the reactor so that we can design a better and more efficient solar to hydrogen reactor converting solar energy to hydrogen. And another topic that we are currently working on is hydrogen and hybrid energy storage system. In this project, we are looking at using a hybrid storage solution combining battery and hydrogen to store the variable renewables, for example, solar and wind, so that we can stabilize the grid as well as provide greener solutions for the consumers. And the third topic that we are working on is natural gas valorization. In this topic, for example, we are converting natural gas into ethylene so that we can decrease the energy consumption as well as increasing the selectivity for ethylene production using methane oxidative coupling in a membrane reactor. In today's talk, we're focusing on the first topic, which is the hydrogen production technology and system, and tell you more about how we use an oxygen permeable membrane to enhance the hydrogen production from water. We know that why we are talking about hydrogen these days, because there are more and more attention are now on hydrogen. Recently, if you're following the energy news, you know that Germany actually will release this 9 billion euro plans to use hydrogen to recover their economic. And also in US, in Europe, they are developing this hydrogen strategy or hydrogen roadmap for the economic development. And also in Canada, we are also developing a national hydrogen strategy, which could be different from the US because US is looking at hydrogen from their coal. But here in Canada, we have a lot of renewable electricity, and we also have a lot of fossil energy. So that will be a great chance for us to use these energy resources to produce hydrogen for the economic. However, hydrogen's role as an energy carrier is not a very new topic. It's more than 100 years old. From the 1900s, the Danish scientist Polar Kuhl, actually the first one, built an electrolysis system to store the wind power in the stormy days so that they can use this hydrogen to power some systems for the days without wind. Here is the historic photographs of this electrolysis cell in the basement below a wind turbine. 10 of these tubs were built. On a windy day, they can produce around 1,000 liters of hydrogen and 500 liters of oxygen per hour. That is around 3 to 4 kilowatt systems that was built in Denmark. And these gases were stored and then they were used, for example, in lighting, which is commercial use, as well as for welding. So they can use both this stored hydrogen for commercial energy supply as well as industry. So this inspired a British scientist called Haldane, so who hypothesized this type of new system that can actually, there will be a different power stations that locates at very suitable distance, so they can convert the excess wind energy to hydrogen, and then to store the hydrogen in these power stations, and then to convert it back into electricity when there's no wind. And this is actually further inspired another professor in US, who is the first one to use the term hydrogen economic in 1970s. And so Professor Bockris in TAMU in United States, so he envisioned that US could be supplied by solely on solar energy with hydrogen storage. From that time on, we know more about hydrogen in the energy carrying industry as well as different renewable energies industry. So that's why there are more and more hydrogen products coming to the market. So for example, Germany in the 1990s actually had the first solar power hydrogen production plants. And later we see a hydrogen fuel cell car as well as hydrogen fuel cell buses running around the globe. And also in 1999, Europe has the first hydrogen fueling station in Germany. So this will make you think that hydrogen is actually very important an energy carrier. However, if you look at the hydrogen consumption these days, it will shock you because we are using hydrogen mainly for chemical industry. So from this pie chart, you can see that more than 50% of the hydrogen these days is for ammonia production, which will further produce the fertilizer using this ammonia. And 1/3 of the hydrogen is utilized in refineries. So we want to upgrade our crude oil to increase the quality of the crude oil using hydrogen. So only very limited amount of hydrogen is utilized in the energy carrying or the energy industry these days. However, since we're talking a lot more about hydrogen, about renewable hydrogen these days, people envision that in the near future, so from now, 30 years from now, the hydrogen market actually can increase around 8 times, from 10 exajoule to around 80 exajoule. So the hydrogen can be used, for example, for power generation, energy storage, can be used in transportation, for example, fuel cell cars, trucks, trains, etc. And also to provide energy for industry, for building, as well as new feedstocks for the new advanced technologies for chemical industry. So there are great potential for hydrogen in this market in the near future. If you look at where these hydrogen are from these days, and here are the statistics. So on the left figure, you can see that most of the hydrogen these days are from hydrocarbons. Almost half of them is from natural gas, and the rest of them are from coal, oil. So only 4% of this hydrogen is from water electrolysis, which can be qualified as green hydrogen if this electricity is green. And so because now we are calling a lot for renewable hydrogen, sustainable hydrogen, so there will be a great incentives for us to convert renewable energy, for example, solar and wind electricity into hydrogen. And then also, if we are using this fossil fuel, using this hydrocarbon, we have to capture the CO2 that is associated with the hydrogen production. The reason now these days we are still looking at a lot of this hydrogen from fossil fuel is because, first of all, it's because of the cost. So here you can see that there is a comparison of the cost for water electrolysis and natural gas reforming. And water electrolysis is 3 to 4 times more expensive than natural gas reforming. And if you look at the sensitivity analysis here, you can see that the reason that hydrogen is so cheap for natural gas reforming is because the feedstock price is very low these days. And if you compare the water electrolysis and natural gas reforming in a more detailed way, so you can see that you break it down into different feedstock cost, capex, as well as operation cost. You can see that majority of the cost for the hydrogen is the feedstock. It's either electricity or methane in the steam methane reforming case. So that's why it's very important for us to increase the efficiency so that we can decrease the use of electricity or decrease the use of methane so that we can further decrease the cost of hydrogen. Another problem of hydrogen produced from fossil fuel is the CO2 emission. So here we compare two technologies. So one is steam methane reforming, and the other is coal gasification. And you can see that they both produced more than hundreds of grams of CO2 per megajoule of hydrogen. And not only the production that will produce CO2, there is also the compression, the delivery of the hydrogen will also emit CO2, which are shown in this figure. So you can see that this dark solid bar is the production associated CO2, and the others are for compression as well as for delivery. So actually, production can only emit around half of the CO2 for the life cycle of a hydrogen. So that's why there is a lot of potential for us as a researcher to decrease the cost of hydrogen as well as to decrease the CO2 emission associated with hydrogen production. Okay, now let's have a look at the conventional SMR process for hydrogen, which is shown in this graph. Here we have methane and water, which are fed into a reformer at very high temperature to produce syngas, which is a mixture of CO and hydrogen. After that, the syngas will go into the water gas shift reactor to convert the CO to hydrogen so that we can maximize the hydrogen production. After that, the mixture of the products will go into a pressure swing absorption purification reactor so that we can purify the hydrogen to produce high purity of hydrogen and also capture the CO2 from this process. The unrecovered hydrogen and unconverted methane will be fed into a combustor so that to provide part of the energy required by the reformer. So you can see that there are several challenges for this SMR process. First of all, is the hydrogen separation and recovery, which are more stringent these days because we need a high purity hydrogen for fuel cell cars. And secondly, the heat integration of different reactors at different temperature. And you can see that there will be a lot of heat exchanger that is required to capture the heat integration. And the third is the CO2 capture, so that we can capture the CO2 from this process and store it and produce hydrogen without carbon footprint. So in order to tackle this challenge, we propose to use a membrane and intensify the entire process into one unit reactor. Here we use an oxygen permeable membrane for this process intensification. On one side, water is split into hydrogen and oxygen passes through this membrane to the other side to oxidize the methane to produce water and CO2. So you can see that the hydrogen can be separated from the water very easily by condensing the water, which is the same for the CO2 and water mixture on the other side of the membrane. And since we are in one reactor, the heat transfer is actually highly intensified so that we can enhance the heat integration in the entire reactor. We did some analysis to compare these two processes for hydrogen production, which is shown in this graph. Here you can see that by process intensification in this membrane, we can actually increase the efficiency from 76% to 82%, which is 6 percentage point increase. So you might be wondering, what is this magical membrane? So now let's zoom in to look at this membrane. So this membrane that we're using is the mixed ionic electronic conducting material, and which is usually doped perovskites or dual phase composite. So here's the process again, that we have water producing hydrogen and oxygen. Oxygen diffuse through this membrane and then will react with the methane to produce water and CO2. So if you look at this membrane, it's actually a dense membrane, so there's no pores. So that's why we can achieve very high selectivity of oxygen permeation. So only oxygen can permeate through this dense membrane in the form of oxygen ions. So why is that? That's because this membrane, if you look more closer into these crystals of this membrane, you can see that it's an oxide. So there are lots of different cations as well as oxygen sites in this crystal structure. However, at high temperature and also at reducing environments, there are lots of oxygen vacancies that are formed inside the crystal of this membrane. So that's why the oxygen actually can diffuse through this membrane by hopping through these different oxygen sites. So from one vacancy to the other vacancy, it's like jumping from one side to the other side. So that's why only the oxygen or the oxygen ion can diffuse through this membrane, and other species are blocked out by this membrane. And if you look at the entire process, we can separate them into 5 different steps. So the first step is that the water first diffuse, or water vapor would diffuse to this membrane on the surface of the membrane. And after that, the oxygen from the water will react with the oxygen vacancies to form lattice oxygen, while the hydrogen is produced from this side and diffused away from the surface. So once the lattice oxygen is formed, it will diffuse through this membrane to the other side, driven by the chemical potential gradients. And the oxygen diffuses through this by hopping from one vacancy side to the other vacancy side to the other side of this membrane. And after that, this oxygen will react with the methane to form CO2 and water. And that's when we can capture the CO2 very easily from the methane side. And as I mentioned, that this process is driven by the chemical potential gradient. So that's why we say that on the water side, we have very high chemical potential gradient. We have high partial pressure of oxygen. And on the methane side, we have very low chemical potential, and we have a very low partial pressure of oxygen. And because of this, the oxygen vacancies can diffuse through this membrane from the sweep side to the feed side, while the lattice oxygen diffuse from the feed side to the sweep side. So this is how it works in this membrane reactor. And since this is an oxygen permeable membrane, actually there are different types of operation modes depending on the sweep side. And it can be applied, for example, into distributed hydrogen production or as an energy storage technology. So the first step of this mode that we will say is the hydrogen-oxygen production. So in this case, we have hydrogen, which is produced from water splitting. The oxygen diffused through this membrane, and this is driven by a vacuum. So we'll lower the partial pressure of the sweep side by using a vacuum. So we will dry the oxygen diffuse from the water side to the oxygen side. So in this case, we can produce hydrogen and oxygen. And if you don't want to use a vacuum because sometimes it's too energy intensive, you can also use an inert gas, for example, using CO2 or other type of inert gas. You can use this as a sweep gas to sweep away the oxygen from the membrane surface to create a low partial pressure on that side for the diffusion. And again, this is also a hydrogen and oxygen production mode. And also, since we have an oxygen source, we can control the oxygen partial pressure, and we can control the oxygen flux to react with the methane so that we partially oxidize this methane into hydrogen and CO, which is the syngas, to produce further produce methanol, for example. And in this case, we can co-produce hydrogen and syngas in this membrane. And if you just want hydrogen, and you can fully oxidize this methane by continuing flowing this methane and continuing utilizing this oxygen. So in this case, you can see that for 1 mole of methane, we can produce 4 mole of hydrogen and pure hydrogen from the water side. And then the methane is fully oxidized, and we can capture the CO2 from the methane in this case. And since we are utilizing this as a fuel or as a reactant that will react the oxygen, we can use different type of fuels. For example, in this talk, I'm going to talk more about how we integrate this with the coal gasification plants to utilize the gasification product, which is syngas, and to produce high purity of hydrogen in this form, in this mode. So before we move on, I'll first introduce the gasification plant and what it is. So here it shows a schematic of the integrated gasification combined cycle IGCC plant with carbon capture. So here is the clean technology to utilize coal, but we can capture the CO2 in a more efficient manner. And here shows the schematic that we have coal slurry that is fed into the gasifier to produce the raw gas at high temperature and high pressure. And the raw gas is a mixture of very different gases, but it's very reducing. You can see that 35% of this is CO and 34% of this is hydrogen, and also some type of impurities from the coal. And after that, this raw gas will be cooled down, and then the dust will be separated and will be fed into a water gas shift reactor to increase the hydrogen production. And after that, the CO2 will be separated from this two-stage Selesso process for the CO2 compressor, and also the sulfur, the hydrogen sulfur from the process will be also separated to produce sulfur in the Claus plant. So after this Selesso process, we have a clean stream of hydrogen, which will be fed into the combined cycle. So we'll have a gas turbine as running at high temperature, and then we'll use a heat exchanger to run the bottoming Rankine cycle so that we can increase the efficiency of the entire coal power plant. And the problem of this, as you can see, that the raw gas has to cool down from very high temperature to almost room temperature from the Selesso process. So there are a lot of heat exchanger around it. And also there are energy consumption for separation. So the Selesso process actually consumes a huge amount of electricity, which I will show later from the results. So in order to improve the efficiency, especially improve the efficiency for hydrogen separation from CO2, we propose to use this membrane. So in this case, we have this oxygen membrane reactor. So on one side, we have the water splitting to produce hydrogen. And on the other side, we use the gasification product as syngas as the fuel so that we can consume the oxygen, or we can drive more hydrogen production. And because we know that the coal gasification has a lot of impurities, such as H2S, so that's why the membrane has to resist this type of poisonous impurities from the gasification products. So what it looks like in a system, it looks like this. So in this case, we have this high temperature raw gas from the gasifier. So it will go to this high temperature membrane reactor so that we can utilize the heat integration from the high temperature gasifier to the high temperature membrane. And after that, using this membrane, we can use the syngas from the gasification to produce water or produce hydrogen from water splitting. So that's why in this case, on the side 2, which is the water splitting side, we produce the pure hydrogen with water as a mixture. And then on the side 1, we have the syngas reaction. And in this case, the only addition to the plant is this isothermal high temperature membrane reactor, and also some post-processing units to increase the efficiency for the plant. So we use the counterflow configuration to maximize the conversion of this hydrogen. And you can see that, so this is what we mean by counterflow. So the syngas is flow from the left to the right, but the water is flow from the right to the left. So the reason we want to use this counterflow is because, as I mentioned earlier, this process is driven by the potential gradients across this membrane. So that's why we will have high oxygen partial pressure on the side 2 and low partial pressure on the side 1. And the lowest partial pressure of oxygen on side 1 is the inlet, so which is plotted here. So in order to make this membrane work, the side 2 partial pressure has to be above this blue line. So that means that it has to be in this region, in the shaded region. And we also know that when water is splitting, we are producing hydrogen. So the partial pressure of oxygen actually drops when the water is split. So that's why we can decide what is the maximum water splitting rate in ratio in our membrane reactor, which is around 55%. And on the other side, it's very similar. That's the maximum partial pressure is at the inlet on the water side, and the lowest and the lower partial pressure is from the syngas side. But when the syngas is oxidized, the partial pressure of oxygen increases, as shown here. However, we can see that even though we have almost full conversion of the syngas into CO2 and water, we still have a potential gradient. So that's why actually the syngas conversion ratios can be very high. It can be as high as 99%. So after we know that the maximum conversion in our reactor, and then we can build a model for this system. So that's why we use Aspen to build this model to evaluate the performance of this new cycle. So we define the first law efficiency of this plant as the net work output of the plant, electric output of the plant, over the heating value of the core. And the net work output is defined as all the turbo machinery. So all the work is produced by the turbo machinery minus all the auxiliary consumption, work consumption, such as pump, CO2 compression, oxygen separation, the Selexo separation process, etc., etc. So we calibrate our Aspen model with the existing very detailed gasification IGCC plant. And we can see that our model, although it's simplified, it matches very well with the very detailed results. So that's how we use, we decided that means that our model is trustworthy, and we can use this Aspen model to compare our systems with other type of systems. So that's the results. I show here that we compare the CO2 flow rate, the CO2 captured ratio, as well as the combined cycle auxiliary load for different. Reference plant is the IGCC plant without CO2 capture. And the IGCC WGS is the conventional IGCC plant with CO2 capture using water gas shift reactor as well as the Selexo process. So you can see that our new Novo designed the IGCC OTM process using an oxygen transport membrane actually can decrease the auxiliary loads by a lot. So that's why we can improve the efficiency of our plant. And also you can see that because we decreased our auxiliary loads, so that means that our network outputs compare with the conventional IGCC with CO2 capture, we can increase our network output. So that's why we can increase our efficiency from 30%, 30.6% to 34.2%. And we also calculate the energy consumption for CO2 avoided in our plant. And we can see that our new designed IGCC OTM has this value, has the energy consumption almost 60% lower than the conventional IGCC with water gas tube reactor for CO2 capture. So these results again convince us that this new design is actually working. So we can utilize this IGCC OTM process to increase our electricity output, even though when we are capturing the CO2. Then you might be wondering whether this membrane, does it actually work in reality? So that's why we actually in the lab, we designed this type of membrane and tested in a very similar environment. So in the lab, we fabricate a very stable membrane for this application so that it can be very stable even though the environment is very reducing as well as corrosive. So we designed the membrane material that we used is a dual phase membrane material. So, so the chemical formula is showed here. And if you look at the membrane, you look at a microscopic image, you can see that the membrane is very thin, it's 36 micrometer. And we have a catalyst on top of this membrane to enhance the reaction rates. And also we have a support. Because this membrane is very thin, we have to have a mechanical support so that we can increase the mechanical strength of this membrane. And the catalyst is showed in the next slide. So the reason we want to use a catalyst because the surface reaction is actually the rate limiting step based on a model. So here we use different resistance so we assign different resistance for different steps. As I mentioned that there are 5 steps in our membrane process. So each step we assign a resistance on it so that we can compare the resistance. So we know that which resistance is the largest. So we know that is the rate limiting step. So from the modeling, we see that the resistance on the sweep side or the surface reaction is actually the rate limiting step. So that's why we have to apply the catalyst on the surface to enhance the surface reaction so that we can have higher hydrogen production rate. And we didn't use precious metal, so we use a nickel on an SDC support as a catalyst. So here we show the TEM image of this, showing you that the nickel and the SDC, actually there are 2 separate phases. And also it distributed very well on the surface of the membrane. And also there's no reaction between this nickel and SDC. So that means that we can keep the stability of the catalyst over a long run. So in the lab, we measured the performance of this membrane. So here shows you the literature results, a literature survey on a lot of different type of membranes. So you can see that we have a lot of different membranes available in the literature. And the maximum performance is around 10 micromole per centimeter square per second, which is around 7.4 milliliter per centimeter per minute. So we measured the performance of our membrane, which is shown in this figure. So if you look at the hydrogen flux or the hydrogen production rates here, you can see that the maximum that we can reach is around 18 milliliters per centimeter per square per minute at 950 degrees C using a reducing sweep gas, which we have hydrogen and CO ratio as 1, because as I mentioned earlier, the gasification product is reducing and has the hydrogen and CO2 ratio as 1 versus 1. So we use very similar gas stats for the gasification, and then to test the performance of our membrane and show that the membrane performance actually outperformed the state-of-the-art membrane in the literature. And we also studied the long-term stability of this membrane under various switch conditions. So for example, you can see that we tested for hundreds of hours under hydrogen, a mixture of hydrogen and CO or hydrogen of CO2. And we also add this hydrogen sulfur as a poisonous gas into the stream to make sure that our membranes can survive this very harsh environment. So you can see that for different sweep gas, because we are creating different type of partial pressure of oxygen by using different sweep gas, so the performances can be different. However, it's quite stable, and so that means that there's no deterioration of the membrane materials over a long run. And also, we characterize the membrane followed the experiments using EDX as well as SEM. And the EDX shows that we don't have sulfur that is deposited on this membrane. That means that the H2S is not poisonous for our membrane. And we also compare the elements ratio of this fresh and spent membrane, and you can see that it's within the arrow of experimental equipment. So you can see that this membrane chemically can be very stable even under this very reducing, very harsh gasification environment. And we did observe some sintering, which is prevalent in high temperature processes. However, from this previous figure, you can see that since our performance is very stable, you can see that even we found some sintering occurs in the catalyst, the performance is not deteriorates remarkably. And that's actually also confirmed that this membrane design is very stable under this harsh environment in the gasifier. So to summarize that I introduce you this type of oxygen transport membrane to produce hydrogen, and we use this IGCC application as example to show you how we can use this OTM process to increase the efficiency and decrease the energy penalty for CO2 capture. And I also show you that we experimentally fabricated this dual phase membrane in the lab using non-precious metal catalysts so that we can make sure that the cost of the membrane is low, and also this type of membrane can perform very stably under very harsh environments in the gasifier. So I would like to thank my collaborator for this work, Dr. Cai Li and Professor Zhu Xuefeng and Yang Weishen at the Dalian Institute of Chemical Physics. And also want to thank Professor Armagodim at MIT, who also contribute to this work. And the Aspen from this study is supplied by Aspen Technology, and then the financial support is the Excellent Cooperation. And thank you very much for your attention. So I'd love to take any questions if you have.
Thank you so much, Professor Wu. So the platform is now open for Q&As. If anyone would like to ask any questions, please go ahead.
Thank you, Professor Wu. That was very interesting. I'm
Thank you.
Interested to see how this R&D can turn into sort of commercialization efforts. Are you doing any, do you have any efforts going on with sort of real world applications for hydrogen production and sort of commercialization?
Yeah, so our collaborator in Dalian, so they're scaling up this type of membrane production process. So as I mentioned, that's this membrane. Let me see. Yeah, so the membrane that we're using is this type of dual phase membrane. So we are not using a very expensive metal. So actually the the source of these metals are very cheap, but the production, all the manufacturing process is more expensive at this moment because it's not scaled up. So we are looking with Dalian that we want to scale up this process so that we can decrease the production cost of this membrane. So that's so we just to commercialize it. Yeah.
Okay. So Dalian has the partnership with the University of Waterloo to explore this production of the membrane?
So we are exploring that, yeah.
Yeah.
So they have the equipment on site that they can produce these membranes in medium scale actually. So yeah.
Okay. I would love to talk further, maybe off this webinar, and see if there's opportunities for us to collaborate also with your work for some applications in Ontario.
Yeah, sounds good. Yeah, I would love to do that.
Okay.
Yeah, thank you.
Thank you very much.
Any more questions we have? I guess
I have a quick question, if that's
yeah,
okay.
please go ahead.
Thank you, Professor. That was such a good talk. I just have a quick question about the counterflow configuration that you talked about. I just wonder if that counterflow configuration can be used for other applications like the production of ethylene as well as hydrogen as well, or is that specifically for the IGCC application?
Yeah, so thank you for the question. So this configuration can be used in any membrane reactor. So the reason we want to have this type of configuration is to make good use of the chemical potential across this membrane. So that we can increase, for example, we can increase the conversion from the water side, as well as increase the conversion of the product side. Yeah, but it can be used in different type of applications.
Thank you, sir. Thank you.
Yeah. More questions? I guess we don't have any more questions. But
sounds good. Yeah.
But please feel free to contact Professor Wu. His email contact information is in the public domain. And if you would like to touch base with him, you can always contact him and ask questions. Professor Wu, I would like to thank you for your wonderful presentation and sharing such wonderful insights with us. Thank you so very much. So I guess
thank you.
that's
it.
Thank
you for organizing this, and thank you for everyone's attention.
Is it okay if someone posts the recording for this after, or?
I will be posting the entire video on the WISE YouTube channel and on the WISE website as well for you guys to view. I just need to do some minor edits, and then it will be available by the end of this week in the public domain.
Thank you.
Okay. Would it be possible to share the slides as well, or is that okay?
Yeah. So I can share that. So all these are published in the two papers that I cite. So I can send you an email.
Great. Thank you.
Yeah.
Okay, perfect. Thank you so much, Professor Wu. Thank you so much, audience. Thank you so much. Have a great day. Okay. Bye-bye.
Thank you.